In the previous section, we investigated limits that either went to infinity or the input went to infinity itself. And we had to work through a lot of algebra and infinitesimal arithmetic to determine what the values of the limits are. In this section, we'll introduce a rule called L'Hopital's rule that will give us a bit of a shortcut in particular situations in which we have indeterminate forms. Quick note, the spelling in the textbook looks more like La Hospital, and that is the Americanization of the name. I'm old school, I guess, so I stick with the French spelling of the name with the accent and do my best impersonation of a Frenchman and say it's L'Hopital rule. Either way, you could say it's La Hospital. Many calculus students think we'll use the hospital to take care of the limit, and either way, the rule is the same regardless of how you spell it. So the setup is like this. In general, we know that, say if the limit as x approaches a of f of x is L, which isn't 0, actually that part doesn't matter, and the limit as x approaches a of g of x is maybe m, and this is more important, it's not 0, then the limit of their ratio of f of x divided by g of x is simply the ratio of their limits of f of x divided by the limit of g of x, which is equal to L divided by m. So easy case, if the denominator is not 0, then the limit of a ratio is the ratio of the limits, and it's just L over m. On the other hand, problems arise if m is 0 and L is not 0, then we can't use this business because because g of x is an so if the limit of the denominator is 0, means g of x is infinitely close to 0 when x is infinitely close to a, and so then the ratio f of x over g of x is an infinite number, right? Because we're taking a finite number, L, so it's not infinitesimal, and an infinite number, or an infinitesimal number, G, and dividing, so it's going to be an infinite number. And so we would know that the limit as x approaches a of f of x over g of x is going to be either plus or minus infinity, and we'd have to go through the exercises from the previous section to determine which sign is it. Is it positive or negative? So in both these cases, we've got the methods of arithmetic with hyperreal numbers to deal with these limits. But more often than not, if you remember in the last section, what happened when m was 0 and L is 0. Then we've got an indeterminate form, because in this case, both f of x and g of x are infinitesimal when x is infinitely close to a. Both of them are infinitesimal, and so then f of x divided by g of x is an indeterminate form. And that's what a lot of the exercises in the past section was. How do you deal with indeterminate forms? We have to do factoring or some kind of business to deal with it. For just a quick example, if I looked at the limit as x approaches 2 of, say, x squared minus 4 divided by x minus 2, then we could recognize, well, this is the same as the limit as x approaches 2, since the top factors is x minus 2 times x plus 2, and the bottom is x minus 2. These guys cancel, and so this is the limit as x approaches 2 of just simply x plus 2, which is a continuous function, and so this limit is 4. That's kind of the algebra that we would work with when we had indeterminate forms, or we could have factored out largest powers. In this case, it was nice because we got canceling. But nonetheless, we had to do some kind of algebra. Well, L'Hopital's rule gives us a method of dealing with these indeterminate forms when we've got the top going to 0 and the bottom going to 0. But first, I've got to introduce a couple of definitions before we can put up the definition of L'Hopital. So first off, a neighborhood of a real number C is just an interval which contains C as an interior point. Then a deleted neighborhood is a neighborhood of C in which C is removed. So in L'Hopital's rule, we're going to examine what happens to a function. Typically, we're looking at a limit as x gets close to C of some function, right? And so we never want to evaluate anything at C because we just want to get close to it. So we just remove that value C from the neighborhood, and in symbols, the interval I with C removed just means everybody in I except for C, right? Pretty simple. Okay, so that's needed here for the definition of L'Hopital's rule. So here's the setup. Suppose that in some deleted neighborhood of a real number C, so we don't care about at C, but anywhere near C, both f prime and g prime exist, and the derivative of g is not 0. And then we'll assume that we're going to have some indeterminate form, that the limit as f of x as x approaches c is 0, and the limit as x approaches c of g is 0. So both, we're looking at a ratio here, right? So we're looking at this limit, and we have that the top is going to 0 and the bottom is going to 0. That's an indeterminate form. Well, L'Hopital's rule says if the limit of the ratio of the derivatives exist or is infinite, then these two limits are equal. And this is going to be super handy. It will speed things up in the calculations of limits. We won't have to do nearly as much algebra or arithmetic with hyperreals. So let me just, right off the bat, just give an example. So let's consider the limit as x approaches 1 of the square root of x minus 1 over, let's say, the cube root of x minus 1. So if we look at the top, the limit as x approaches 1 of square root of x minus 1, this is a continuous function, and as x approaches 1, we get 1 minus 1, so this is equal to 1 minus 1, which is 0. Similarly, if we investigate the denominator, the limit as x approaches 1 of the cube root of x minus 1, still a continuous function, so the cube root of 1 is 1, so it's 1 minus 1, which is 0. So we meet the requirements of L'Hopital, that the limit of the numerator is 0 and the limit of the denominator is 0. Then what L'Hopital's rule says that, well, let's look at their derivatives. Let's investigate their derivatives, and maybe that will help us with this problem. So the derivative of the numerator, square root of x minus 1, well, this is the derivative of x to the 1/2 minus 1, and that's equal to 1/2 x to the minus 1/2. So that's the derivative of the numerator. The derivative of the denominator, which I'll write as x to the 1/3 minus 1, is equal to 1/3 x to the negative 2/3. Okay? And L'Hopital's rule says, okay, if we've got an indeterminate form, the top's going to 0, the bottom's going to 0, then we can say that this is equal to, according to L'Hopital's rule, that this is equal to the limit as x approaches 1 of the derivatives. So 1/2 x to the minus 1/2 divided by 1/3 x to the minus 2/3. And doing some, our basic simplifying here, I've got x to the negative 1/2 next to negative 2/3. So this is the same as the limit as x approaches 1 of 3/2 x to the 1/6. And this is a continuous function. And so we could just plug 1 in, and this is equal to 3/2. No work of having to factor out largest powers of x or do any business like that. All we had to do was compute derivatives. Students tend to find this much more easy than doing all the arithmetic, though that arithmetic is very good to know. L'Hopital's rule really speeds up the process and makes typically indeterminate limits much easier to compute. So in the next video or videos, I'll just run through a number of exercises demonstrating the use of L'Hopital's rule.